right. Well, welcome everyone to today's webinar. I'm Betsy Scott with Construction Instruction, and we've been hearing from a lot of builders asking us how tight is too tight in enclosures. So we wanted to address that with a webinar today featuring Gord Cook from our team, who's going to lead the discussion from a building science perspective. And Bradley Whalen from Aeroseal, who's going to share some of what he's hearing in the field, real experiences builders are having, what they're hearing from HVAC contractors in relation to this as well. I will be on the line throughout, but I'm going to go take my video off for you and let these guys lead the show. At any point in time, if you want to ask a question, we're going to use you can use either the chat or the Q&A. I'll take a look for both of those. And if it's appropriate at the time, I will bring up the question during the conversation. If not, we'll hold those questions to the end of today. But we're really looking forward to this discussion, and thanks so much for joining us today. Turn things over to you, Gord.
Thanks, Betsy, very much. Gord Cook, Construction Instruction. I've been doing blower door testing since 1987 on houses, and this is a topic I always get. How tight is too tight? Where do we want to head with this? So thanks for the opportunity, gang, and it's a quick hour. I will say we'll make the presentation available because I'm going to go through some data, and you're going to go, boy, that was pretty quick. And Brad, you and I are going to have a conversation and add some practicality to it. Maybe just introduce yourself quickly, Brad.
Sure, yeah. Appreciate it, Brad Wallin with Aeroseal. I appreciate you guys setting this up, Gord, and having me part of that. We get the same question all the time from builders too. So I'm glad to be on here and share some of the experiences for builders, for some of the builders that'll be on here and just other people that are interested. So glad to get an expert opinion on how tight is too tight. So looking forward to it.
I recognize a few names on the call who are pretty experienced, and they're going to say, what are we going to chat about today? And I'm saying, well, let's talk the benefits of air sealing, what that can deliver for you, whether that's air quality, comfort, energy efficiency, durability. How are we doing it now? And what are the sort of good, better, best ways of doing that? Some builders are having tremendous success already. Others would struggle. And then what does that do to loads? The tighter we get, what does that do to impact? What does that do to the impact of heating, cooling, ventilation, carbon, so on and so on? We'll talk a little bit about measurement and validation, but that what we want to highlight today, of course, is I'll still call it cutting edge technology. I like to claim, Brad, that AI is the first application, Aeroseal is the first application of artificial intelligence in the building industry, right? It's basically robotically controlled air sealing. Yeah, I don't think there's any other way to put it.
Right.
People often ask, what's AI going to do to us? Well, this is the kind of thing it could do. It could help our labor situation by saying, let's let a robot do this. And it's not a R2D2 robot, but it's a robotic way, a computer-controlled way of doing air sealing. So I'm excited to talk about that. I'll start with, a hero of mine. Harold Orr was one of the original researchers on building science up here in Canada in the 1970s. And Harold would say, we knew how to calculate heat loss through walls and ceilings, but we didn't really know what air leakage was doing. And he and a bunch of others sort of pioneered this idea of let's measure air tightness, let's calibrate that air tightness against energy use. And folks like Gary Anderson at Minneapolis or the Energy Conservatory, that's on the right-hand side, the first of the blower doors. I had the pleasure of introducing the Aeroseal process to Harold Orr a number of years ago as he was being given an award in San Diego for his contribution to EBA, the Energy and Environmental Building Alliance. And there was Harold who took an immediate interest in Aeroseal. In fact, he kind of went like this, yes, finally, in my lifetime, we're going to be able to get to the number that they had set right back in the 70s, which was 1.5 air change per hour at 50 pascals. And I'll give you why that number came about, but that's been in his mind and the minds of most building scientists is kind of the target we'd like to get to in all houses. But I'll show you what that's about. So why airtight? And most of you will have seen this before, but be really clear. The first two reasons that airtightness made its way into the code, section 402 of the ICC and section 932 of the, 925 of the National Building Code of Canada, the rationale for putting airtightness in the code, air barriers in the code, if you will, was to limit the possibility of moisture flow into cool cavities. This there at the top right, this attic moisture problem is the result of air leakage, but also to improve comfort control. So those were the two first things listed in code, to improve comfort and to improve or reduce the potential for condensation in cavities. At the same time, we know it actually improves air quality. That is, you can't control the air quality in a house unless you've got good air tightness. Picture in the bottom right is the wildfire smoke in today's world. It's really nice when you live in an incredibly airtight house. When that wood smoke's coming over, you can go, geez, I can pick and choose when I want to open my windows or turn on my ventilation system. When my house is airtight, I have better control over when I want to bring in outside air. And then thinking about things like noise transmission, and in attached dwellings, odor and smoke control became a bigger and bigger issue. In LEED buildings, for example, the LEED requirements are for air tightness between suites to manage odor and smoke control. And I would say it's obvious that it'll have an implication on heating and cooling loads. All the bottom left picture, the limit entry of pests, bugs, mice, so on, improve energy efficiency. But in my mind, one of the most important aspects is this: meeting the expectations of homeowners. If you asked your homeowners exactly how many holes would you like me to leave in the walls or attics of your house, I'll guarantee you'll get this: holes. What do you mean holes? Why would there be holes in a house? I don't want any holes. But you're going to say on the right-hand side, what about ventilation? Right. What about fresh air? Well, let's be really clear. We never got fresh air through electrical outlets. We got fresh air by opening windows. And in today's world, it's been code now for at least 20 years to put in mechanical ventilation. So the excuse we get is that we want to make houses leaky so that we get fresh air. That's not the way code approaches it. Code approaches ventilation and fresh air by operable windows and mechanical ventilation. So fundamentally, your clients don't want to be wasting any energy, and they certainly don't want bugs, noise, dust, neighbors, fumes, and so on getting into their house. So first and foremost, it's really about meeting the expectations of homeowners. That's pretty critical. That said, it is in the code. There's 17 phrases, and it's been in the code since the 1990s. And here we go, continuous air barriers, sealed, caulk, sealed, 17 times. It directs you, and homeowners, frankly, have this. I've been in court cases where the homeowner brings out, or the lawyer for the homeowner brings out this list and says, Mr. Cook, you were at the house. Did you feel air leakage underneath the baseboard of my daughter's bedroom? Yes. Well, then it couldn't have met code because it's supposed to be sealed. And they have a point to make that these prescriptive, subjective requirements lead you into a bit of a risk. If you're not doing air tightness testing, if you're not doing processes such as Aeroseal, you are subject to potential liability because of the expectations driven by code. And it's if somebody's saying, well, what about commercial codes? Well, again, it's been in ASHRAE standards, ASHRAE 90.1 since 2010. Air barrier designs, notice designed and constructed with a continuous barrier to air leakage. Really interesting that this is where we would like to get to. And if I said there's, the details of that in section 543 of the air barrier installation of 90.1, really clear direction of where I should be sealed, all of the elements that I should be speaking of. So it's been a code requirement. If your trades are saying, why are you making me do this? Because it's in the code. It's been a code requirement. You need to do this. You need to show that element. So all of those elements. Brad, you will know that Aeroseal took upon themselves to contact Ecotrope, the largest provider of for energy raters and the software and the verification. And they shared air tightness data from various places. And if we said 3 air changes, it's not, is the code in climate zones 3 to 8, that's the dotted red line. And notice all of those houses in climate zones where 3 air changes is a requirement. And yes, there's a couple of climate zones where it's not. Climate zones 1 and 2 is 5 air changes. But notice the tremendous variation. And Brad, I know you're relatively new to the industry. Your experience with this in chatting with builders, did this surprise you, the variation in air tightness?
Yeah, it certainly did. And I think that for me, having a fresh perspective was, I didn't know anything about this either, as a homeowner, but coming into this and talking to our builder partners and the construction teams, I guess I was just kind of personally shocked at one, how many different kind of trades were involved trying to, work on air tightness, and then also just the mass confusion and frustration on not being able to get to these targets, especially when climate zone here in the Dallas Fort Worth area, when it went from 5 to 3. I mean, it just seemed like a straight panic. And being involved in Aeroseal, I'm like, well, there's a tailor-made solution here that's super easy. So I don't understand why there's such frustration. We have an easy solution here, but that's I guess that's part of our job here, is to educate our builders on what we do and our ability to easily help them. But yes, to answer your question, I mean, I was just as surprised as a lot of people were on how difficult this is for some people.
And so this was thousands of houses, different climate zones between fall of 2022 and the fall of 2023, a snapshot of houses. Notice down at the bottom right, Minneapolis seems to have figured this out. And frankly, you would say, I wonder why they figured it out. Well, that was the first place in the country way back in the 70s, 80s to increase insulation levels. And we'll chat about the link between increased insulation levels and air tightness. And they came about it organically and have found systems, methods. They would say they can meet 1.5 air change per hour. They can certainly meet the 3 air change per hour pretty quickly, but clearly other places haven't quite figured out where we need to get to. And I do want to say, from a code perspective, back to the code, and then from a practicality standpoint, air tightness was tied to insulation levels. The key to understanding here is the more insulation you put in an attic, for example, or a wall, the less drying potential there is in that wall, right? Heat flow through the wall created tremendous drying potential. And it means the backside of the cavity is colder and colder. So imagine in Minnesota, Chicago, going from R20 in attic to R40 and now to R60, the attic just got colder and colder. And that means the underside of the roof deck, it got colder and colder. And if any warm, moist air is moving through the insulation, it gets super cooled and gets to the point where it wants to condense on the first hard surface it is. So in climate zones where they've started adding insulation, they recognized, oops, when we add insulation, that causes interstitial condensation in above grade walls, in attics. And that's where why air tightness made its way into the code. Not because people often say, well, we have to make them airtight. We have to make them airtight when you add insulation. Every time you increase insulation, you want to think about increasing your levels of air tightness. A good example of that is the Passive House program that looks for extraordinary amounts of insulation in attics and walls. They also have an extraordinary air tightness level of 0.6. Those two are commensurate. It makes total building science sense. If you're going to put R100 in an attic, you want to be even tighter than what, let's say, a common code built house was. But the whole reasoning behind the 1.5 air changes was that even at high levels of insulation, like R60, R30 in walls, the chance that any one leak, if I'm at 1.5, the chance that any one leak is big enough to cause interstitial condensation is dramatically reduced. But the more insulation you put in the walls, the tighter it needs to be. And that's true of every climate zone. So keep that in mind, that initial number of 1.5 ACH was tied to the increase in insulation. And here's just a little example of that, a little animation. When more moist air gets into a wall cavity, goes through the insulation and touches a cold surface, such as the backside of the sheathing, you're going to get condensation. And so there's two ways to attack that. Well, maybe three: stop insulating walls so the walls stay warm. Well, that's not going to happen. Two, make sure that no warm, moist air ever gets in the cavity. That would be what we're talking about today. Or three, you could add the first condensing surface, you could add insulation to it. You could add insulation to the outside of the building. All worthwhile things to do. That is both things, air tightness and continuous insulation. But fundamentally, you don't want warm, moist air coming into contact with cold surfaces. So that's the code derivation, if you will. And understanding that the pictures we're showing here are the result of air leakage. Sometimes we hear folks saying, no, it's because the house was too tight. No, it's because the house wasn't tight enough. Warm, moist air leaking into cold cavities, condensing on the inside of that cavity with no way to escape. That's all air leakage. That's why it's in the code. And because of that, air tightness testing is really helpful, because if you don't test, you don't know, to allow you to compare air tightness levels, to predict moisture and energy impact. And I am going to show you some data that's going to show you how do we predict these things. What does this look like, at least at a big broad brush? What might the impact be on houses? So many of you will have seen a blower door test before, where you do the testing way up on the right-hand side there at 50, 60 pascals of pressure, 5 to 8 readings that you take at different levels. Well, that's a pressure, that's an air tightness level or an air leakage level at 50 pascal of pressure, which is roughly 20-mile-an-hour wind on all sides of the house at one time. That's clearly not the way the house leaks every day, but how would I determine how much air is leaking in and out of a building? And the blower door, the manufacturer's software, gives you this curve, this line that helps predict at lower pressures, more normal pressures, what the air leakage might be. But what's nice is it's fairly simple math. It's demonstrative, right? Of when you take a house up to that 20-mile-an-hour wind to find those holes, it allows you to validate those air barrier details. So a big advocate of testing. I love the stress and the angst when I bring the red door up and people look at it and go, geez, you're going to test my houses? Yes, we should test our houses and do those measurements, and then allow us to extrapolate that line. And it's pretty straightforward math. And blower doors, this happens to be Energy Conservatory. There's other great manufacturers as well, Retrotech and others. But they basically have a pretty simple formula of how they turn the fan pressure into a volume of air that's moving, and then down at the bottom of the right, I turn that into, at 50 pascal pressure, what is the air change rate? And I've already hinted to you, your number should be, you want to aim for 1.5, but that's fairly straightforward math. Now, to extrapolate that, to figure out the energy impact or the moisture impact, you need now to extrapolate that down to a pressure that would be considered more normal. And typically, depending on your climate zone, you're going to use 5 pascal or 10 pascal pressure. That is when you think about average wind pressures, stack effect, that is convection loops rising in air, mechanical pressures. ASHRAE has said 5 pascal is probably the right number. And then you would use a series of algorithms to turn that into energy use. And I'll show you, oops, sorry, that got out of whack, my apologies. But I will show, some of the math. It is fairly tricky math. It's what's called the effective leakage area at 5 pascals of pressure. The stack coefficient, that is how tall is the building, how cold is it outside, wind coefficients, design wind speeds, all of that. This is called the Lawrence Berkeley lab formula that tries to take the air tightness test and turn it into what's leaking on a normal day. And we're using 5 pascal as the measurement for that. And so imagining the different effects overall, what's happening in that house, holes leaking in, holes leaking it out, what's the actual number. Now, it's a predicted number. It's not a real number. We don't know exactly how a house leaks, where the holes are, but that's the math that's done. And you can see here on the blower door test, it's showing the effective leakage area at 4 Pascal and 10 Pascal. What it's saying is this house at an air change rate up the top there of 4.11 has a leakage rate at 4 Pascal, sorry, leakage area at 4 Pascals of 86 square inches. And at 4 Pascals, how much air might come in or out of that building. That's how we determine the air tightness impacts on energy bills, if you will. So just a little example of that. And so, sorry, just go back to that quickly and say, so that's the predictive models that help us determine energy performance. What I want to show is, what would it do from a moisture perspective? Remember, I talked about moisture in wall cavities? Let's do that one. So I still use the extrapolation down to a typical pressure and turn that into an algorithm for the using the content, moisture content of air is kind of fascinating. Oh, I don't know why these got screwed up. My sincere apologies for that. And I'll fix those before I send them out to you. So if I said to you, let's use an example of a 2,350 square foot house at 20% RH and use a 5 Pascal pressure as an average in that house on a, let's say on a cold winter's day of 5 Pascal pressure. And so if I showed you there, that's working better now. If you notice that roughly at 5 Pascals, we're getting about 150 CFM of air leakage. That's under a negative pressure of the blower. Presumably under normal pieces, about half of those holes would be leaking in and half of those holes would be leaking out. So that's 75 CFM of air leaking in or out. And if we think of 75 CFM of air times 60 CFM times 24 hours, would be 108,000 cubic feet of air moving through our houses, through the walls and ceilings of our house on a given day. And that air would contain roughly, and I can't see it there exactly, but this amount, what does it say there, Brad? I can't read it on my apologies. What does it say there for the amount of moisture? Maybe it's hidden. I'm hidden by everybody's picture. I'll go down to the next level. It's basically 24 pounds of water or 24 pints of water per day. I just want you to put that in. Just think about that for a second. 24 pints of water per day in vapor form, transported by air, moving from inside your building to outside your building on this day. Or in Houston, maybe coming from outside to inside, depending on which way the wind is blowing and so on. 24 pounds, 24 pints of water per day. If the inside relative humidity is 40% RH, that could double to as many as 48 pints a day. Now, are we seeing that as a problem? Well, where's the leak? How big are the holes? So on and so on. And this is a house that it's at, is still at levels of air tightness around 2 air changes per hour. So imagining the control of moisture in an envelope is really, really important to our overall conversation. So one, we do it for energy. Two, we do it for moisture transfer, and we want to see the implications of that. And then think about the impact on multifamily, the fact that we're now connected on 2 or 3 sides to our neighbors, and what would that mean from a noise control, an odor control, or the HVAC system, the ventilation requirements in those buildings, and the impact it would have. Just in these buildings, imagining on a cold winter's day, air's leaking at the bottom of buildings and leaking out at the top, which means everybody at the lower levels, suites 101 and 102, are breathing parking lot air or perhaps outdoor air. Maybe 201 is breathing outdoor air, but those suites, those folks who are in suite 401 are breathing everybody else's air. And so air tightness and compartmentalization is vitally important to this conversation. So we have an energy impact, a moisture impact, and we have a noise and odor impact as well on our houses. So there are also really good reasons why air tightness is important to us. And Brad, what we really want to talk or get to is, how have we been doing air sealing up till now? And you've seen this. It's beads of caulk, tapes, foams, so on. And that's, I guess, what gives us the variation. You noted earlier the number of trades, the different trades that are involved in this. I'm sure you talk to them all the time. What are you hearing who's doing the air sealing work? Whose scopes of work is it in?
So typically, if we're not involved or before we get involved, it's usually split between the insulator and the painter is typically what we've heard. So there's a little bit of scope in each of them, and they all hate it, and to be honest with you. So I mean, it's a tedious task. I mean, and it's just the guess and check, and you don't even know if you've done a good job till you test it at the end. Well, it's a frustration for everybody. It
You
was a
think
frustration.
Right. You think about the hundreds, maybe thousands of lineal feet of top plate, bottom plates around windows, around penetrations, so on and so on, depending on the houses. So it is that's kind of what we're using. And we use a series of materials. Sometimes we're using on the left there sheet goods or fluid applied products on the outside. In the middle, gaskets, tapes, caulkings, foams, all imagining compatibility, making sure that they're compatible with the substrates they're working on, versus on your side, this spot application of the sealant just going where you need it. Because you can lay hundreds of feet of tape across a seam that may in fact not be leaking at all. This is important to understand. And are we using the right material in the right location? And this all has implications on labor and cost, and I'm going to say carbon release, that is greenhouse gas emissions of the types of materials that you're using, the sprays and so on that you might be using that might have a high carbon content versus using a spot application where it's a very small amount of material that's going into the building. So pretty powerful. And you've already spoken to, but maybe speak again to some of the challenges, Brad, that you've been seeing.
Well, again, it's just the manual process and how tedious it is, and just not being able to guarantee that you've done a good job, and then you do your air sealing, you throw your drywall up, and you didn't do a good job, you didn't pass, then what, right? Then you're calling Aero Barrier, and we said, well, we told you to do it during construction, but we'll save you this time, but we got to start doing it during construction. It's a tailor-made solution for air sealing, and as you said, Gord, it only seals where there's leaks, right? The science takes over, the technology takes over, and it does its thing. It just makes things so easy.
And that is the challenge, right? And as an example, here in the north, we often use vapor barriers or air barrier, polyethylene vapor barriers, air barriers. We see some sheet goods being used in PASFOs. And we often find lots of beads of caulking. And if you look carefully at that picture, even not too carefully, you'll recognize that every one of those beads of caulking is a complete waste of time. The beads between the studs, although the building official may like to see it, that's not leaking any air because it's covered by a sheet of drywall on one side, a sheet of OSB on the other side, and it's covered by a sheet of plastic. The only place we really need the beads are at seams. And even the ones where you see the horizontal line, the seam there, that's not going to work very well because you need to clamp those beads of caulking, and there wouldn't be any clamping in the middle of those stud bays. So we see contractors, and I appreciate them doing the work, trying to do the work, but a lot of it is wasted effort. Cases and cases of caulking and so on. And again, I respect the trades for trying it, but often it's misdirected. And we see these kinds of things as well. The wrong material being used on the top right there, using a spray foam on the top plate there. And unfortunately, that's not going to seal in that location. That should be a bead of caulking, and it should be a continuous bead of caulking. Down at the bottom, it's not a continuous bead. Was it dirty that day? Not sure why the drywaller's insulator in this case wasn't able to make a continuous bead. But we'll see lots and lots of examples of these kinds of things. Well-meaning, exact the wrong product, the spray foam. I often ask, why are you using foam there? Expanding foam. It's not a spray foam, expanding foam. And they say, well, the gun comes nice and long, so I don't have to reach down. I can just use it. But frankly, it's the wrong material, right? One, it's in the wrong location, and two, it's not doing an air seal in that location. That would have to be a bead of caulking in that location. So Brad, I'm sure you see this. You have some understanding of pricing that these folks would be getting for this, the air sealing packages. What do you hear out there is what builders are paying for their air sealing package?
mean, it really varies. I mean, prior to us, they call it advanced air sealing packages, and I mean, really, I mean, it's you know, $400 or $500 per trade that they add to their scope to try to do some of these things. And to your point, that it's just not. They're trying, and I get it. It's not a knock on the attempt because it's just very difficult, right? Trying to do that manual process. So we're able to automate it. We're able to, when we work with our builders, we take a look at some of the costs that they're incurring now, and we try to get our solution to be a no cost add or a very low cost add to what they're doing now, and actually take care of the issue and guarantee it for them every time. So that's always the part of the analysis when something goes into a build, what things can come out, and if there's things that are going in that aren't really working, well, those are great to come out anyway. So
And we see this kind of thing where people, okay, go nuts on this. And again, on the left, really the wrong material. And in places that's not leaking air, right? This on the right was an air sealing method brought up by an insulation company. It was a good attempt, but again, it was thousands of dollars and really didn't add significantly to the air tightness because the beads of caulking are going, or the beads of foam are ending up in places where there's no expectation for air leakage there anyway, and missing some of the most important places. So lots of wasted effort. Again, just examples of things that aren't working very well. And even spray foam, we see challenges. Spray foam's really good at the big holes. I love spray foam, and I think it's very valid when you think about the big holes, but not necessarily enough on the small holes. And for example, on that wall, the bottom plate to the floor assembly, that would still have to be sealed. So I'm not suggesting don't use foam. And Brad, I think you would agree that nothing wrong with spray foam is a great insulation product, but it doesn't necessarily get you to the levels of air tightness you want. You've shown this picture. This has been your experience.
yeah, and so on a house like that, we would go in the iteration. We would go want to go right there. The lid's already on it. You got a fairly tight envelope with with the spray foam, but you blast Aeroberry at that point, that's the perfect scenario. You're gonna get the best bang for your buck there, and you're gonna have you could take a house like that down to passive house levels, 0.6 air change per hour. So that to me, if you do a spray foam and an Aeroberry, that's gonna be the tightest, best house you're gonna get.
But for those on the call who are using spray foam, you would say, okay, that still has implications. I can imagine that the spray foam's doing the big holes, the Aerobear is doing the Aeroseal's doing the small holes. Best of both worlds is pretty powerful.
Yeah.
And then let's talk about the application. You mentioned it before. It's kind of 2 times that we see people are doing the Aeroseal process. Just work through that with us.
Yeah, so if you do spray foam application, we can go before drywall because, like I said, we can pressurize the space, and the lid is on the house at that point, and it's tight enough where Aerobear can do its thing and work. If you're gonna do a bad insulated house, we want to go after drywall. Um, something jumped up on me here on my computer. Want to go after drywall in that situation. That's the best. You're gonna get your best air leakage bang for your buck on that. So really, it can be it works well with spray foam, also works well with that insulation.
And you kind of made the point. The house has to be able to be pressurized. So the
Yeah.
lid's got to be on, the attic hatch has to be in, your windows have to be in. The odd time you'll get a temporary door in place and you go, okay, I'll work around that. But the house has to be, the enclosure of the building has to be more or less complete in order to get it done. So that's pretty useful. And then I talked about the multifamily suites, and one you would say do the entire envelope, but then pretty interesting to think about individual suites as well. Just talk us a little bit about that.
Yeah, we do a lot of that work, more and more of that, and there's more and more multifamily, buildings hitting the market, and those typically leak really a lot, right? They have a lot of shared walls, a lot of shared spaces. There's a lot of issues there. It's really tough for these builders to get down to 3 or even 5 ACH. So we do a lot of that. A lot of these individual units will start at 10, 12 ACH. Well, there's just no way that you can get down to code. So AeroBear works really, really well in that situation. And we just go down the hallway and spray those units onto the tear down and go to the next one.
And so it's a very quick process, and I'll give you the plug that it's really dramatic in terms of we've used it in retrofit situations, townhouse. I mean, it's not ideal when people are there, but townhouse situations where there's a smoker on one side and an unhappy person on the other side, and it's
Right.
difficult to restrict that. The lead buildings would say limit or don't allow smoking in buildings, but frankly, that's not always acceptable. And even if it's cooking odors and so on. So important to understand the benefit. And as you've indicated, exterior buildings for a number of reasons is typically better than the interior. And some would say, well, I already have fire and smoke control. That must be airtight. And surprisingly, we're not finding it as airtight. The materials certainly are good materials. The drywall that they're using, for example, the fire resistance are good, but it still comes down to the small holes that we're interested in. And I thought we would just have you walk quickly through the process. We'll just in a few minutes give a sense of, and I think I've got an animation of it as well, but if you wouldn't mind, just a quick post
Sure.
for those who haven't seen it.
Yeah, this is a good slide. I mean, the air barrier sealant is some intellectual property, within that sealant, special type of sealant that starts as a liquid. We get to the house, we set up a typical retrotech blower door. We start pressurizing the house with the seal stations in the house. We have a main control unit that's talking to those seal stations and starting to spray that itemized sealant. It goes from a liquid to basically a fog, an Aeroseal fog. Because the house is pressurized, the air is trying to find leakage points, and as it's doing that, it's taking this sealant with it, and that's where the magic starts to happen, right? That fog starts to coagulate like a blood clot. I've heard people say it's kind of like fix-a-flat for a house, right? It's kind of an interesting way to think about it. So that fog just starts coagulating and turns into a traditional um, caulking, really. And that last photo on the right is really interesting. Gives you a good idea of where that air pull would be on that electrical box is around it, of course. That's something that maybe you could manually seal that. It's tedious though, and not that much fun. But what is really cool about how this technology works is look inside that electrical box. I mean, you can see in the knockouts there, it seals right in there. There's air pull going in there. So that's impossible to seal manually. So we like to say death by a million cuts, and that's really how the technology works. It starts to go to all these really micro leakage points and starts to seal it up, places that you never be able to manually seal or even know was leaking, right? So that's the cool part. And then the other thing that is really neat about it is it's happening in real time, and you're seeing it in real time, and we know when we leave the house where it is from a leakage standpoint. We set up the system. It starts at, for example, this house started at 8 ACH 50, and within an hour and a half, we had it down to 0.6. So in real time, every 10 seconds, you're getting a real time reading. If there's an issue, our guys can go in there, and if there's a big hole or something like that, they'll shoot it with a little cam foam, and before you know it, you're down to a really tight air level. So
It's that report. I just love that, as you say, real time. Betsy, it looks like there might be a question that you'd like to pose. Oh, you're on mute, Betsy.
Thank you. I was trying to keep quiet in the background here. Just a couple of questions have come in so far, comments. How do you seal can lights? Is there anything different that you do than what you were showing with the outlets in that image?
no, same process. The technology will just, if there's an air pull there, which typically there is, that's one of the leakage points. They'll start pulling in there and start coagulating, and it takes care of it.
And then how does it work with occupied units?
Well,
So
one.
yeah, we like to call those rescues. Aero barriers is really best done in new construction, right? We have done that for builder partners where they get to a point where they didn't use it to start, and perhaps before we got involved, and they're failing. So in that instance, you have to cover up any horizontal surfaces. So anywhere there's an air pull vertically, it'll start to seal and coagulate. If it doesn't do that, it just falls to the ground and kind of turns into a drywall dust within 30 minutes. But if you're doing an occupied house, you got to cover up your flooring and your cabinets and your wrap your fixtures, basically like prepping for a paint job, right? So it's a lot more work. It's unnecessary work. It just needs to be done during construction.
Yeah.
And then you have an evangelist here who said, in their own opinion, Aeroseal works best when it's applied after sealing the plates. Openings and sheathing is done, not the fix a hole solution like you're talking about. And that many of them achieve, so they validated your 1.5 and said mostly they achieve less than or equal to 1 air change per hour. So that's awesome. And then what's the maximum size of a hole it can close?
Half an inch is what we say that's roughly what it is. So our during construction, our guys will go in there. You start to pressurize house. You can see some of the big holes and whatnot. We'll hit that with some foam and whatnot. And guys will go in during the seal actually, because you can really see once it's fogged in there and it's pressurized and the air's starting to move around, the sealant's moving around. If there's a big draw into a certain area, there's a big hole, we'll get in there and can foam it a little bit just to help speed the process up.
Okay, we have a couple other comments here, but I'm going to go offline for a minute. I'm going to hold those. So if you have a question or a comment, feel free to keep putting those into the queue. We won't forget you. I just want to make sure we get all of the bases covered before we bring some of those other questions to light.
Yep. And so I'll continue on and just say, and to Brad's point, you could seal a hole bigger than a half inch with AeroBarrier, but you don't want to. It's going to take too long and too much sealing. You might as well do that with a quick shot of foam. It's really, thinking about the smaller holes, those holes that still cause damage in terms of moisture intrusion and so on, into wall cavities, but really ideally designed for those smaller holes. And then just showing some of the pieces of equipment. You have dealers across the country that are using this equipment, Brad, servicing pretty much all of North America, as I understand.
Yep, so that's true. And on the AeroBear side, we've started to do the work direct. So Aeroseal, the model's changed a little bit. There are legacy dealers out there, but for the most part now, we're all Aeroseal employees. Aeroseal's acquired a lot of the dealers just to do the work direct, to really train people the right way, to price things aggressively. We're under $1 a square foot, which I think is one thing that we've really has been a challenge. I think when AeroBerry hit the market, it was quite a bit more expensive, right? But the models changed. We're able to be really aggressive with our pricing now, and the technology's gotten better. It's gotten leaner. It's just how technology works. We've gotten more efficient, and then we've been able to pass those savings along to our builders. So it's really a cost-effective solution for whether you're building 1,000 homes in a market or you're building 10. It's really a great option.
And then we're seeing some of the examples of that sealant, as you mentioned, and it's paintable. People often say, is it going to be visual? And to some extent, it's hard to find it, right? And so just some examples on the page here of before and after seal, what you're looking for. And it's basically looks like a slightly grayed caulking that's in the same places where you'd want the caulking to go anyway, and just gets rid of the labor. I'll say again, it's like a robot doing all of the caulking and sealing for you. So that's pretty useful. We do have an animation that will run quickly that we can talk over, and just Brad, in terms of setup, what kinds of things are we looking at doing?
Yeah, so we're gonna cover up any of those, anywhere we don't want the sealant to go, right? So operable parts of the windows, the fireplace openings, we're gonna plug the boots, and because we want the sealant to go around it, not necessarily into the boots. And there's a seal station getting set up. So every 500 square feet or so, a seal station, is set up. Then we set up in the garage and we pressurize the space with the blower door, just like traditionally, just like your energy air does at the end to test it. Same, exact same process. There's, the fan, which is pressurizing the space, the main control unit, as I mentioned, software control. That's an automated system, allows us to monitor the seal. We start pressurizing. There's a positive pressure going into the space, and then that main control unit starts talking to all those seal stations and starts spraying, right? And then the software at that point takes over, and as the technology is doing its thing, as the sealant's getting to these leakage points, we're watching the seal and watching the house get tighter and tighter. And then, like I said, our guys can go in there, they mask up. It's a really actually, it's Green Guard Gold certified. It was product of the year years ago. Low VOC off gassing, so less than less than commercial paint or hairspray. So really, healthy product. But so our guys go in there, and this is a good example. You can see it go on the top plate, windows and doors, the leaks. If there's at that point, if their guys are in there and there's a big hole, they'll see it, and that's when they hit it with a little bit extra foam, so speed things up. But as I said, we're watching it in real time, so
And
we
you can
have a
just, I found it fascinating when we first did it. A builder was doing it and he said, well, let's go to 3 air changes. And we got to 3 and he said, well, why don't we go to 2? Okay, well, let's go to 1.5. And it's just a matter of running the machine a little longer and
yeah,
finding those spots. Pretty interesting, right?
yeah.
You did say it's pressurizing as opposed to depressurizing. Most energy raters are doing a depressurization test. So the number is going to be slightly different, pressure versus depressurization. So it's not an exact equivalent. And of course, you did have to tape off some things like window sashes and vents, which when you open those back up, your result's going to be slightly different than, say, what the energy rater does. Is that, I think we know that to be.
Yeah, that's true, Gordon. You know what we've started to do for our builder partners now, if they want to, is we actually pause the seal, take down that prep, and then get our final reading ends up being a lot closer because we reintroduce that leakage from the windows and whatever we had prepped off, but we pull that off, and then by the time the rater goes in there, the house actually gets a little bit tighter in theory, right? As long as no one's punching holes in the wall, it gets a little bit tighter when you start putting trim in and carpet and whatnot. So the delta, we get pretty good with our builder partners. We know what that delta is. We know if we
We're on mute there. Yeah, I missed you there. But we get the idea. I think we'll move on, but that's fine. And then there are potential offsets, right? That you start thinking about, could I take out some of the manual caulking, foaming, and tape rework? Could I think about redoing, reconsidering the thickness of continuous insulation? That is, take the improvements in air tightness and apply it against other energy measures. I'm not necessarily suggesting you do that, but just if you're trying to optimize the performance of your house and looking at cost, air sealing is the most important thing to do. And once you have your tightness under control, you can start thinking about trade-offs or optimization, both in terms of material costs and certainly in terms of labor is where we'd like to get to. So that's pretty powerful. I want to go back to that comparison of those of various markets and think about all of those houses that are to the right, if you will, of the that air tightness line. We want to be to the left of that 3 air changes. And how do we get all houses built everywhere to be under 3 air changes? In fact, you heard me say you really want to be lower than that, 1.5 from a moisture perspective. So moving that that air tightness line to get more and more houses to that level. And as a little example of that, there you have Minnesota. It's done a nice job. Everything's under 3 air changes. Not everything's under 1.5, and it should be. They have this great history of air tightness because of the early research that was done there, because of the moisture issues in attics and walls, and because of good industry training. They did a nice job, and without this kind of technology. But if you look at just a few hours away in Chicago, but they've really struggled. Shouldn't the air tightness goal be the same in that climate zone? Where are we really trying to get to? And would we consider challenges in these houses with moisture entrapment in walls, poor heating, cooling control, poor moisture control in those houses? So just want to encourage you to think about what number should you be at. And I will agree, there's going to be energy raters on this call who are going to say, well, code says 3, that's all I got to do. Fair enough. From a code perspective, you're at 3. Or they might say, well, the energy model doesn't really get me much benefit if I go tighter. Well, look again, if you model a house correctly, it's still an incremental benefit from 3 down to 1.5. And I would ask all energy raters to play the true role of building scientists. Exactly how many holes do we want in our walls or attics? How much moisture do we want in the wall? Is really what we need to think about. Tighter is better, and start encouraging your builders to not just meet code, but let's go beyond. And we know, again, there is a benefit if you do get tighter, as Brad was indicating, there are some other trade-offs that you can use. I thought I'd show you a pretty busy slide here, and we're near the end, but I wanted to show you the impact of air sealing improvements on HVAC loads. Start at the bottom, which is Minnesota, which is the largest, which is basically in terms of heating load reductions, which is the middle column, 0.75 tons. So roughly 10,000 BTU change. So in a heating load reduction, about 10,000 BTUs. That's basically a furnace size, right? You go from a 50 to a 60, a 60 to a 70, basically one furnace size smaller, from 5 air changes down to 1.5. That'd be true in Chicago and other places. What I wanted to indicate is the cooling load reduction, say in a Houston or a Phoenix. We often get confusion. Well, if I make my house tighter, the tonnage is going to go up. No, the tonnage is going to go down. So we'd see about a 1/4 of a ton reduction, maybe as much on, this is on a typical 2,300 square foot house. So it may be more than that. What's most important in the Houston and Phoenix, not Phoenix, but in the Houston market is, what about the moisture associated with that air leakage coming into those? We showed moisture challenges in cold climates. In fact, in cold climates, you want to reduce air leakage so that the moisture stays in the house, it's not on the wall, and so that you don't have to humidify a house. But in Houston and Atlanta and Raleigh, what we really want to do is think about the moisture that could be in those walls. I do want to highlight, though, this slide was part of a carbon presentation that we did, a carbon reduction, greenhouse gas emissions, very significant greenhouse gas reductions. This is based on the total operational carbon of a house, and showing that we can see a really nice percentage reductions, 4 to 13% in greenhouse gas emissions associated with making houses tighter. So really nice that we get there. But I'm just highlighting here the Chicago market, the design heat loads. When you go from, say, 3 air changes at 40,000 BTUs, that's on the left-hand side, down to 1.5, a small change in heating load reduction, and also a change in cooling loads. So nice little reductions in heating and cooling loads to help you rationalize those sizes. I wanted to show you the Houston context. In Houston, if you look at the potential humidity sources inside of houses, you have the moisture created by the occupants, top left. You have the moisture coming in via natural infiltration, which we're talking about today. You have moisture via mechanical ventilation. You have vapor diffusion through the building, and you have the moisture in the building materials. And you'll notice that a big controllable source is 50 to 90 pints per day in a loose home at 5 air changes per hour, potentially coming inside the house through natural air leakage, depending on wind and so on. It's one of the biggest sources of moisture. And if I apply good strategies, I can reduce the risk of high levels of humidity in humid climates specifically. Doesn't have to be southern climates, but in humid climates in the summer, I can dramatically reduce the potential for humidity problems. And just as a little example of that, by creating tighter houses, by going from 5 down to 1.5, which is my recommendation, everybody should be looking at 1.5, you're saving in the order of reducing your humidity load by 30 to 50 pints per day. That's basically a dehumidifier. That is a portable dehumidifier. Not to say you don't still need a dehumidifier, because you still have other loads, but a dramatic reduction, if I can get from 5 air changes down to 1.5, that's pretty powerful. We're nearing the end, but Betsy, did you have a quick question? You're on mute again.
For a couple of comments, and this is actually quite timely since you mentioned ERVs there related to indoor air quality. Wendell says some builders are concerned that the ERV or the air in the home is becoming stale or not healthy. How do you reassure builders that have a tight house is not a negative as far as air quality? He's seen statements saying inside air quality is 3 or 4 times worse than outside air. How does that fresh air work in multi-units?
So that's really the point, isn't it? That we need to control fresh air. We've always had ventilation in code. Ventilation in code started in the 1900s, and the ventilation system back then was windows. we had windows and we knew how to use them. We've stopped using windows because of noise, dust, security, energy costs, air conditioning, humidity loads. We've stopped using our windows, and our codes have said since at least the 1990s that we need mechanical ventilation. So when I hear somebody say, well, air quality is going to be compromised, I'm going to say, wait a minute. You have two ventilation systems in your house, windows and mechanical ventilation. You never got fresh air through electrical outlets. You don't want that. You don't want air coming in through your garage walls, through the attic. You want fresh air coming in through either windows or through a mechanical ventilation system, then it's controllable. And the minute you realize, oh, I already have control over my ventilation, bath fans, ERVs, then there's no excuse to make a house tight. It really speaks to this slide. I love the John Candy. I'm a John Candy fan, but I've had people say to me, we really should drill some holes in the walls. I'm like, really? You want holes in your walls? Why would you want that? Well, I need fresh air. Right. Then open a window or turn on the energy recovery ventilator. I don't want to leave the impression that you're making houses tight, therefore you need ventilation. No, it's the exact opposite. You need ventilation. And once you understand ventilation, then you can go ahead and make houses as tight as you want. There's really no need. There's no redeeming value of having unwanted holes in walls or attics. And if it's an air quality thing, think about that wood smoke situation, the wildfire smoke. The best possible scenario is you live in an incredibly tight house. You have a mechanical ventilation system that has a HEPA filter on it or a MERV 13 filter, which most ERVs now do. And if it gets really bad for short periods of time, you can turn off the ventilation system. You're not being impacted by the outside air. So be really, really clear. The tighter the house, the better the air quality control you can have, because you can control the amount of air that's moving into the house, and you can decide and filter pollutants that might be coming into that house. So think about it as we finish up. If every house was under 1.5, you'd be meeting the expectations of clients. You'd stop wasting time and materials. You take the angst out of, right, that blower door test. I'm showing you the bottom left. This was a house that's day of closing or just before. It's all hands on deck, including the senior VP of construction of a large national builder, all watching the blower door test results, running around the house with beads of caulking and foam, trying to get the house under 4 air changes. And we would have said, take away that angst, do it up front, use this automated procedure, if you will, streamline your production, and ultimately optimize humidity control and the HVAC loads. So I know that's a short session, but Brad, I want to thank you. Obviously, you're available. We are available for a few questions. We have maybe a minute or two. Betsy, any final questions?
There are 3 quick process related questions. The first was, do the installers wear hazmat suits when they're doing the
No, they don't need to. We have them put on a 3M respirator mask and go in. But like I said, Green Guard Gold Certified Product of the Year. It's got really low VOC off gassing, so it's a very healthy product.
Another is, in new construction, do you recommend applying Aeroseal before or after the actual doors and windows are placed?
You need to have the windows and doors in there, because you need to be able to pressurize the space. So if there was no windows or doors, you can't. The hole's too big. You can't pressurize the space. You need that positive air pressure to get the air moving and getting the air forced to the leakage points.
But you would tape off the sashes and because you
Yeah,
don't want the ceiling getting into the operable sections of the windows.
correct. Yep.
Okay.
Exactly.
And then the last one related to that is, can you just quickly repeat what is done at the end of the seal to get the Aeroseal report ACH to be closer to what the EA test report ACH will be?
Yeah, so it's just a removing of the prep, right? So if we tape off those windows, like Gord just said, we don't want sealant get into the operable parts of the windows. We're gonna tape the bottom part of the door. That taped off the fireplaces. So what we'll do at that point then is pause the seal, go in and take down all that prep. Because at the end of the day, we want our number on our report to end up being very close to what your energy rater is gonna um, show at final, right? So it's just reintroducing that leakage.
And then there was one last our two last questions. Would this need to be done prior to or post texture?
Either. It's totally fine. You can do it after. It won't stick to the walls, right? It doesn't stick unless there's a hole, an air leakage point in the wall. It's going to go in there and seal that at the back, but it's not going to. It just bounces off vertical surfaces. So you can do it after paint or texture.
Perfect. And then the last thing is, what is capacity for install on a daily basis?
So our crews are set to do 2 single families a day. The prep is about an hour-ish, and then the seal is an hour and a half to 2 hours. So we have our crews set to do 2 single families a day. Multifamily units, if you're up there in an apartment and you can knock out, go 1, 2, 3, 4, 5, you can get done 6 to 8 multifamily units in a day.
Perfect.
And then that would just mean multiple crews or multiple rigs if need be
Yeah.
on a busier site than 2 a day.
Exactly. Yeah. So, and we have 40 crews here and 42-man crews here in the Dallas-Fort Worth area, just for an example. So.
Great.
So Brad, thanks very much. Hopefully people found that interesting. I'll just leave a bit of a challenge. How many holes do your customers want you to leave in the walls or attics of their house? Where are codes headed? Where's the energy standards going? How much noise, dust, bugs, odors, as my brother said, when his house was 26 air changes per hour, and I showed him the size of the hole in the house. He said, "Do you think that's where the mice are coming in?" And he was really pleased when we built the family cottage and we got down to 0.4. He said to me, "So no mice in this house, right?" I said, "Exactly." So think about where we want to head with this. 1.5 air changes per hour is a great number. Some are going to say, well, 2 is good enough. Okay, fair enough. But you make that decision. But I always think about, is there any redeeming quality to have houses tighter? No. The challenge has been we just didn't have the time or the technology to do it. Now that we have the technology, and now that you can do it with basically no time involved, no trades involved other than the Aeroseal folks, why wouldn't we go ahead, push the easy button and just get our houses under 1.5? Lots of opportunities when you know that every house is going to be at that level of air tightness. So hopefully that helps. Betsy, thanks for hosting. Really
Yes.
appreciate it. As I mentioned, we'll find a way to get folks a copy of the presentation with those two arrows that I had out of place. I'll have those fixed.
Absolutely. I will take care of that. We've got all your information and look for follow-up from us in the next several days. In the meantime, have a great rest of your day. Thanks for spending some time with us.
Thanks, Brad.
Yeah, everybody. Yep. Thanks, guys. Bye-bye.